Welcome to lecture 13, where we discuss the algebraic theorems on limits. To make the discussion on algebraic theorems more compact, let me introduce the extended real line, the extended real line, which is the set indicated with R bar given by R union minus infinity plus infinity. In other words, we are now assuming that minus infinity and plus infinity are two symbols that belong to the extended real line. This makes provides a more compact representation for the limits. So we can write now an tends to L as an element of the extended real line, so that we can not only represent convergent but also divergent sequences. So in other words, with this expression we can represent limits of type 1 convergent, but also type 2 divergent to plus infinity, and type 3 divergent to minus infinity. Now that we have these extended real line, we can try to extend to R bar the usual classical operations. So the classical operations on real number, namely the sum, subtraction, multiplication, and division, can be extended to R bar. How? Well, by just intuition, we can say that, for example, 20 plus infinity is equal to plus infinity. The same way we can say that 7 times plus infinity is equal to plus infinity, or plus infinity times plus or minus infinity is equal to plus or minus infinity, or minus infinity times plus or minus infinity is equal to minus plus infinity, or 5 divided by plus infinity is equal to 0. There are some operations, however, that cannot be defined. And these operations are plus infinity minus infinity. This is undefined. 0 times plus or minus infinity, multiplying 0 by plus or minus infinity, or dividing plus or minus infinity by plus or minus infinity, or dividing a number 7 by 0. All these remain undefined. So that implies that in those cases we need to devise a new method to find the limits. This doesn't mean that the limit does not exist. It is only that we are now ready to state the algebraic theorems on limits. Let us given two sequences of real numbers an and bn such that an tends to L1 in the extended real line, so can be a convergent or divergent sequence. Bn tends to L2 into the extended real line. Then we can say the following. Let's call this first theorem. An plus Bn will tend to L1 plus L2. So this is saying that the sequence given by the sum of the two sequences will be convergent to the sum of the limits. An minus Bn tends to L1 minus L2. An times Bn tends to L1 times L2. An divided by Bn tends to L1 divided by L2. And this is only valid if the operation on the right hand side is defined. So this is like saying, for example, that this fourth theorem saying that an divided by bn tends to L1 divided by L2 only if L1 divided by L2 does not fall in one of these undefined cases. We have another proposition that is part of the theorem saying that if lambda is a real number different from 0, then this implies that lambda an tends to lambda L1. Okay, before starting the proof of the theorem, let's make some observation. Okay, so let me start with the observation 1. If the operation on the right hand side is not defined, which is just like saying that the right hand side, for example this one, is one of the undefined cases, for example can be this product or any other type of or undefined case. Well, in that case we have an undeterminate form. So these are also called undeterminate form. Undeterminate forms. And if this happens, which is of course not to be confused with the behavior 4. Remember that behavior 4 stands for the not existence of a limit. We are not saying that. We are saying that when calculating the limit, we end up in one of the undetermined form. Now, in this case, it only means that the limit cannot be calculated from L1 and L2. For example, an plus bn is not gonna be L1 plus L2. This would be false. And we need to resort to some other method. To find an plus to find the limit of an plus bn. To give an example of this, just to show that if we end up in one of the undetermined forms, we cannot calculate the limit by using the original limits L1 and L2, let's consider the case 0 times plus infinity. Okay, let's consider this case. So we are saying that basically an tends to 0 and bn tends to plus infinity. Okay, so what is a possible situation where this happens? Well, if we have an equal to 1 over n, certainly this will tend to 0. And bn equal to n to the square, well, certainly this will tend to plus infinity. But in this case, an times bn will be equal to n that will diverge to plus infinity. Let's now consider an equal to 1 over n squared and bn equal to simply n. In this case, we are still in the case 0 times plus infinity, because an will tend to 0 and bn will tend to plus infinity, but the product an times bn in this case is just equal to 1 over n, that clearly will tend to 0. Again, let's consider an equal to 1 over n and bn equal to, for example, 15n. In this case, the product an bn is just constantly equal to 15, so clearly this will remain 15 also in the limit. Again, an equal to minus 1 over n, this is a sequence that converges to 0, and bn equal to n to the square, the product an times bn in this case is equal to minus n that will diverge to minus infinity. And finally, if an is equal to minus 1 to the n divided by n, and bn is just equal to n, we have another situation where an will tend to 0 and bn will go to plus infinity. But in this case, and we will prove of only some cases of the algebraic theorem. As you see, there are many possible cases we can prove but we will just limit ourselves to some that are in a way more meaningful to us. Okay, so let's start with the first case where we have an that tends to L1, and we are assuming now that we have a convergent sequence an, so L1 is a real number, Bn is another convergent sequence to a real number L2, and we want to prove that an plus bn will converge to L1 plus L2. Okay, so this is what we would like to prove. This is basically the theorem that says that the sum of two convergent sequences is a new sequence that will converge to the sum of the limits. Now, before giving the formal proof, let's get some idea, okay? And I will be writing now in green to represent the fact that we are trying to approach the idea of the proof just by intuition, and then we'll formalize this later. Okay, so what we wish to prove is the following. We would like to prove that for every epsilon larger than 0, okay, the difference between L1 plus L2, which is the final limit, and the sequence an plus bn, which is the sum of the two sequences, will be less than or equal to epsilon definitively. This is what we want to prove. However, we know that we can rewrite the same thing as follows: L1 minus an plus L2 minus bn, and this seems to be useful because we are now extracting from the expression two binomials, two differences which may be put in relation with the single limits L1 and L2. In fact, we see that basically this will be by just applying the triangular inequality. So let me remind you what is the triangular inequality. Let me just use the green, okay? So this is the triangular inequality that basically says that if you have the absolute value of x plus y, with x and y be two real numbers, this is less than or equal of the absolute value of x plus the absolute value of y. Okay, so the two real numbers that we are considering now are L1 minus an and L2 minus bn. So we can say that this is less than or equal L1 minus an plus L2 minus bn. But we know that definitively these are less than epsilon divided by 2 plus epsilon divided by 2. So we can find basically an integer n such that after that integer, the first term, the absolute value of L1 minus an, is going to be less than epsilon divided by 2. The second term is going to be less than epsilon divided by 2, which in total will be epsilon, and this will conclude the proof. Okay, so now that we get the idea, let's start the formal proof. Okay, formal proof now. Okay, what is the number? Let's try first to limit the first sequence. We can say that there exists an NA in the natural numbers n such that L1 minus an will be less than or equal of epsilon divided by 2 for every n larger than and A. This is just a definition of the first limit. We are just using the definition of AN to be a convergent sequence to L1. Same way for the Bn sequence, there exists an NB in the natural numbers such that L2 minus Bn is less than or equal epsilon divided by 2 for every n larger than or equal NB. Then, therefore, we can say that for every n which is larger than or equal to the max of the set NA and NB, if n is larger than this max, then both of these conditions are verified. So we can say that the difference L1 plus L2 minus AN plus BN, and now we use the triangular inequality, this will be less than or equal L1 minus AN plus L2 minus BN, but again this will be less than or equal epsilon divided by 2 plus epsilon divided by 2, which is epsilon, and this will conclude the proof. Okay, let's now prove the theorem. Before moving to the other theorems, it is useful now to state another important result, and this is the result I wanna prove now, and I will be using this later. This will simplify the later proofs. Okay, if AN converges to a real number L, then AN is bounded. We remember what is the definition of a bounded sequence. It means that all the elements of the sequence are within minus b and plus b, where b is the bound for the sequence. Okay, so let's give a proof of this result that will be usable later. Now, if AN is convergent to a real number, by just using the definition with epsilon equal 1, we have that there exists at least one n0 into the natural numbers, such that for every n larger than or equal to n0, it must be that AN will be in between L minus 1, L plus 1. So what we are saying is basically that if L is the limit, for every n larger than or equal to n0, the elements of the sequence will be within this range, okay? Will always fall in this interval. Okay, but then if we can say that AN will be, so every element of the sequence, this is going to be true for every natural number n, will be in between small m and capital M, and now we define capital M to be the max of all possible values attained by the sequence A. So A0, A1, A2, dot dot dot, until A to N0 minus 1. This must be in a finite number, okay? So we have a finite number of the elements of the sequence from A0 to AN0 minus 1, in total N0. Because we know that starting from N0, the element AN0, they will fall within this interval. So certainly they will be to the left of L plus 1. Similarly, we can define small m to be the minimal between the same sequence, A0, A1, A2, dot 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 a n0 minus 1. And because we know that from n0 onwards all the elements of the sequence will be within this interval, so they will be certainly to the right of L minus 1. So with this we know for sure that every element of the sequence will be bounded on the left hand side by small m and on the right hand side by capital M. So we can conclude that the sequence is bounded. Okay, so now that we have this theorem, we can well, one final observation. So we are saying that, so this theorem is saying that if the sequence an is convergent to a real number, then we say that an is bounded. The opposite, of course, is not true. So this is maybe worth mentioning with an observation. If an is bounded, we cannot say that an tends to a real limit. Okay, so this is totally wrong. Okay, this is wrong. And an example of this is an equal to minus 1 to the n. Clearly, this is a sequence that takes value minus 1 plus 1 minus 1 plus 1, so it is bounded, but we know that this has no limit. Okay, so we are now ready to state one of the other theorems, algebraic theorems, and we want to prove now that if an is divergent to plus infinity and bn is convergent to a real number L, then we want to prove the theorem on the sum of the limits. So we want to prove that an plus bn will be divergent to plus infinity. Okay, so we want to prove this theorem now. Okay, so how can we prove this? Now, since bn converges to L, a real number, then by applying the previous theorem, the one that we just proved, we can conclude that bn is bounded. So that implies that there exists at least one k real number such that the absolute value of bn is less than or equal to k for every natural number n. This is just a definition of boundedness of a sequence. We now wish to show that an plus bn diverges to plus infinity, or in other terms, that for every m real number, the sequence an plus bn will be always exceeding m, and this will be done definitively. Okay, but we know that an will diverge to plus infinity, or in other words, there exists some n0 into the natural numbers such that for every n larger than or equal to n0, then we know that an will be exceeding any limit, okay, and in particular will be exceeding m plus k, and this will happen basically definitively. But that implies what? That for every n larger than or equal to n0, the sum an plus bn, because an will be larger than m plus k, this will be larger than m plus k minus k, because the worst thing that can happen at this point is that bn will be minus k, right? Because we know from the first statement that Bn will be always in between minus k and plus k. So in the worst possibility, okay, Bn could be minus k. So we can say that An plus Bn is larger than or equal n plus k minus k, which is just equal to k. But this basically proves the statement, namely the fact that An plus Bn will diverge to plus infinity. Okay. Let's prove another statement, another proposition of another algebraic theorem. Let's assume now that An will converge to L1, real number. Bn will converge to L2, another real number. And then we want to prove that An times Bn will converge to L1 times L2. So this is what we would like to prove. Okay. Now, again, what is the idea behind this proof? What we would like to show is that at some point we need to consider L1, L2 minus An, Bn. And now, whenever we have to deal with the products, we have a trick to apply, okay? And this trick always works, which is just introducing a mixed term, okay? And I'll show you how. For example, I can say L1, L2 minus L1 Bn plus L1 Bn. I'm subtracting and adding the same term, L1 Bn, and then I'm left with An Bn. Okay, so what we have now is we can factor out in the first two terms L1. So we have L1 times L2 minus Bn. And then we have L1 minus An times Bn. And you see what was the reason for introducing the mixed term, because now we have in this expression two terms, L2 minus Bn and L1 minus An, that can be put in relation with the original limits. So now we can again use the triangular inequality, and we can say that this is less than or equal of L1 times L2 minus Bn plus L1 minus An times Bn. And again, this is nothing else that equal, this is what? This is equal to absolute value of L1 by just using the properties of the absolute value of the product of two real numbers times L2 minus Bn plus L1 minus An times Bn. Okay? And now what happens is that, you see, this term is small for large n. Okay, we know that Bn will definitely get closer and closer to L2, so this difference will become smaller and smaller if n gets larger. The same way, this difference is again small for large n. So that's the idea. The idea is that we can make these two very small, and this is bounded basically because of the boundedness of, because Bn is a convergent sequence, so we know that by the previous one of the previous theorem, this is going to be bounded. So we have a good chance of making this right hand side of the inequality as small as we want. And in fact, what we would like to do is making this basically less than or equal. We would like to make this less than or equal to epsilon. So we can say, for example, that suppose that Bn will be bounded by some b. We would like to have in this position what? Epsilon divided by 2b, right? Because multiplying these two terms, we get epsilon divided by 2. Now the same way here, we would like to have epsilon divided by 2 absolute value of L1, because multiplied by L1, this will provide me another epsilon divided by 2. By summing them up, we get exactly epsilon. So that's the idea. Right, so we are now in a good position to give the formal proof of this. So let's attempt. Let's start by observing that Bn converges to L2, a real number. So we know that Bn is bounded, which is to say that there exists a real number b such that for every natural number n, Bn in absolute value is less than or equal to b. Now, for a given epsilon larger than 0, we can say that An tends to L1, another real number. This implies that L1 minus An can be made less than epsilon, less than or equal epsilon divided by 2b for every n larger than or equal some na into the natural number. Okay, and this is basically what we were mentioning before. So we can make the absolute value of L1 minus An less than or equal epsilon divided by 2b, with b being the bound for the sequence Bn. Similarly, Bn tends to L2 implies that we can make L2 minus Bn less than or equal epsilon divided by 2 absolute value of L1 for every n larger than or equal some nb. And notice that, of course, let's make a remark here. And this, we might have a problem if L1 is 0 or b is equal to 0. We will deal with this later, but for the time being, let's suppose that L1 is different from 0 and b is different from 0. Well, in that case, for every n larger than or equal to the max between na and nb, we have that L1 times L2 minus An times Bn by just applying the same transformation, the same trick of inserting the mixed term. We can write that this will be less than or equal of L1 in absolute value times L1 minus Bn plus absolute value of L1 minus An times Bn in absolute value. And now we know that this will be less than or equal of absolute value of L1. We know that the absolute value of L1 minus Bn is less than epsilon divided by, sorry, this is L2, not L1. Sorry, this is L2 clearly. We know that this is less than epsilon divided by 2 absolute value of L1. and we also know that the second term is going to be less than epsilon divided by 2b times b. And clearly, this is just equal to epsilon, which concludes the proof. So the only thing that we need to fix at this point is the case where L1, for example, is equal to 0. Now, I will only consider the case, so let's call this special case L1 equal to 0. We are not considering the case b equal to 0 because, well, clearly if we have a sequence, right, if we have a sequence with b equal to 0, this sequence is just the only sequence that is bounded with b equal to 0 is the constant sequence 0. So this is just something that we can avoid to consider. This is just a trivial case. But let's consider instead the case where L1 is equal to 0, which is just like saying that AN will tend to 0. Right? But this implies, by just applying the definition of limit to this convergent sequence, we know that the absolute value of AN, well, this is basically AN minus 0, right? We know that this is definitely less than or equal some epsilon divided by b. We can make this, and this is definitively true. But that implies that the product AN times BN, okay, because we would need to subtract what? L1 times L2, but at this point this is equal to 0, so this is just the absolute value of AN times BN. But this is now less than or equal what? Well, we can say that this is less than or equal the absolute value of AN times the absolute value of BN. But because AN is definitely, this is just an equal sign. Okay, we have an equal sign here, but this is now less than or equal epsilon divided by b times b, which once again is just epsilon, and this concludes the proof. Okay, right, so the proof